Hello everyone. So in the last class we looked at a bunch of equations starting with the continuity equation, the momentum equation. We derived another equation from the momentum equation by invoking continuity as well, which is the Poisson's equation. This was an equation for pressure that involved the Laplacian of pressure on one side and a nonlinear term on the other side. And then we had the equation for a conserved scalar, like a passive scalar, like temperature, that would be used only if required. And I gave an example that if you have some kind of a fluid flowing that is hot and there is heat transfer involved, then you would need to consider that equation. Otherwise, the continuity and momentum are all you need. And the Poisson's equation, which is again a derived equation. So today, again, we are going to look at another derived equation, which is called the vorticity equation. It is an equation that governs the vorticity. Now, vorticity is defined as the curl of velocity. What do I mean by curl? It is the cross product of a gradient operator and the velocity vector. So naturally, the vorticity is also a vector. So here you have u, which is a velocity vector, which is u1, u2 and u3, isn't it? Similarly, you will have vorticity, which is again omega 1, omega 2 and omega 3. So why are we considering vorticity? Because one of the features, attributes as we called it for turbulent flows, is that it is rotational. You cannot have an irrotational turbulent flow. It is always rotational. That means it has non-zero vorticity. So vorticity is always going to be non-zero in a turbulent flow. Because of that reason, we have to think about vorticity as well. Again, it's a derived quantity. So vorticity is the curl of velocity. So it is defined as del cross u. And I can derive the governing equation for vorticity by taking the curl of the Navier-Stokes equation, curl of the momentum equation. And you will see that this is that equation here when I take the curl of the momentum equation. So I want to show how we can get that. So I will consider for convenience, I will consider the vector equation here. And my momentum equation is ut plus u dot del u equals minus 1 over rho del p, and I am going to consider kinematic viscosity here, so nu del squared u. Unsteady term, convective term, pressure gradient term and viscous term. Now what I do is I take a del cross of this equation. So del cross of the Navier-Stokes equations. And then what I'll have is del cross ut becomes omega t. This is again a vector. Of course, u is a vector. And then I will have del cross, I'll have this u dot del, very complicated part. And then I will have on the right hand side minus 1 over rho del cross del p plus nu, kinematic viscosity, and del squared, I'm flipping the operator here. So del squared del cross u. That's what happens. So most of it is straightforward. I have the rate of change of vorticity on the leftmost side. Now let me pick up the easier ones first. This term here, what will happen to this term? It is going to go to 0. Why? Because curl of a gradient is 0. Curl of a gradient is 0. Del cross del any scalar, del cross del any scalar is 0. Essentially, del cross del phi is equal to 0. Then I have this one here, the rightmost side. So nu del squared del cross u. Obviously, del cross u is the definition of vorticity. So this becomes nu del squared omega. So most of it is figured out. I have this term to figure out. Now this is not as straightforward. And what we'll do is, I want to write this convective term u dot del u in a different form. I will write that as, okay, and I can use vector identities. You can find this online as well. Half del u squared. I'm not going to go into the derivation of this, but I'm going to write it directly. I'm just going to use a vector identity and write the convective term as such. So half del u squared. As you can see, this is del of u squared. This is a gradient of u squared. So obviously u squared is a scalar. Of course, u squared is the magnitude of the velocity vector. So u squared without the vector sign on top, I am indicating it as a magnitude. So it is the magnitude of the velocity vector, isn't it? So that is essentially, I don't need a square root because I've put in a u squared. That is essentially u1 squared plus u2 squared plus u3 squared. That is what u squared is. So I have a half del u squared minus u cross del cross u. Okay, so then I have half del u squared, and this is minus u cross omega, because del cross u is omega. That's the definition of vorticity. So u cross omega. Now, if I take a del cross of this term, I will have half del cross del u squared. Isn't it? Half del cross del u squared minus del cross u cross omega. This is going to go to 0 because of the same reason as I had showed earlier. However, the pressure gradient term, when I took the curl of the pressure gradient term, that went to 0. In the exact same way, this term is also going to go to 0 because del cross del phi is equal to 0. And then I have, what I'll do here is, I will make this a plus and write this as del cross omega cross u. I can do that. I just flipped the cross product and made the negative plus. This part right here is a triple cross product. It's a triple product. Okay, so then if a triple product can be written as 4 different terms. It is u dot del omega minus omega dot del u plus omega del dot u plus u del dot omega. 4 different terms. Now here what I would have is, okay, there are a few terms that are going to go to 0. This is going to go to 0 because of the incompressible assumption, isn't it? Del dot u is going to go to 0. Then del dot omega is going to go to 0 because del dot del cross u. Remember, divergence of a curl is 0. Divergence of a curl is 0. Curl of a gradient of a scalar is 0. Divergence of a curl of a vector is 0. So that's what I have. So I just have 2 terms. So now I put it into my the vorticity equation, and I'll have omega t plus u dot del omega minus omega dot del u equals nu del squared omega, isn't it? The third term on the left hand side, I will just take this to the right hand side and make that positive. So, and combine these two and write it as the total derivative. So I have d omega dt equals omega dot del u plus nu del squared omega. This is my vorticity transport equation. I have d omega dt plus omega dot del u plus nu del squared omega. That is my vorticity transport equation, as you can see here. The nu del squared omega is the vortex stretching term. We have discussed this. The vortex stretching term is known to be one of the primary mechanisms for turbulent flow. How the vortices get stretched and broken up into smaller and smaller vortices. The breakdown happens because of vortex stretching. If you consider two-dimensional flows, this vortex stretching term goes to zero. In that case, how will you justify the existence of turbulent flows? That is why we say that there is no 2D turbulence. We have discussed this as well. This term goes to zero. How is that? So quickly, this velocity vector is u1, u2, u3. Omega is omega 1, omega 2, omega 3. Omega by definition is del cross u, isn't it? So if in 2D u is just u1 and u2, if you take the curl of this vector, omega would be just omega 3. That's it, nothing else. In which case, the vortex stretching term is not going to exist. So I made a mistake here. I marked the viscous term as the vortex stretching. I'm sorry, it is omega dot del u. I was saying omega dot del u. So let me just erase that. It is this term here, omega dot del u. Right? So I have this vortex stretching term is going to go to zero because I am taking omega dot del of u. Omega has only one component. So if you write it out, omega dot del u is going to be equal to 0 because u is only u1, u2 and omega is only omega 3. So you have essentially omega 3 dot u1, u2. Since there is no third component in the velocity and since there is no first and second component in the vorticity, this dot product will turn out to be 0. That is the reason why the vortex stretching term goes to 0 in 2D, which means turbulence does not exist in 2D because vortex stretching is one of the primary mechanisms for the material line to be stretched and broken down into small vortices. So that is about the vorticity transport equation. Now let's look at the role of rates of strain and rotation. So if I consider the velocity gradient, right, which is del ui del xj, these are components of a second order tensor. So any tensor will have, say, because I have u1, u2, u3 and x1, x2, x3, I'll have del u1 del x1, del u1 del x2, del u3 del x3, del u3 del x1, so on and so forth. And I'll have multiple components like that. So I have a second order tensor, 3 by 3, 9 components. So any tensor can be broken down into 3 parts. An isotropic part, which is the diagonal part, and a symmetric deviatoric part, and an anti-symmetric part, or a skew symmetric part. So that is what we are doing here. We are taking the velocity gradient tensor, del ui del xj, splitting it into isotropic, symmetric, and skew symmetric or anti-symmetric. The isotropic part is like the velocity, is like the divergence of the velocity. So it is del dot u. Why? Because it has, remember this velocity gradient would have del u1 del x1, isn't it? And del u2 del x2 on the diagonal components and del u3 del x3 as the diagonal components. Then here I would have del u1 del x2, del u1 del x3, and here I would have del u2 del x del u2 del x1 and del u2 del u3 del x1, and so on and so forth. So I'll have 9 components like that. I didn't write out the 9 components, but you will have 9 components like that. And here, that the diagonal terms is what is shown here. That's the isotropic part. Then I have the symmetric deviatoric part, which is the strain rate tensor. Then have the anti-symmetric part, which is the rotation tensor. So let's look at the strain rate tensor first. So Sij is a symmetric strain rate tensor given by this: half del ui del xj plus del uj del xi. That is the symmetric strain rate tensor. And the anti-symmetric rate of rotation tensor looks like this: half del ui del xj minus del uj del xi. Earlier, when we looked at the stress tensor, we wrote it as an isotropic and a deviatoric part, isn't it? It's the same thing. I have the stress tensor tau ij being written as a isotropic part in terms of pressure, and then 2 mu Sij. The 2 is coming because of this half here. So I hope that is clear. All I did was I took the velocity gradient tensor and split it into 3 parts: the isotropic part, the symmetric deviatoric, and the skew symmetric or the anti-symmetric. Now, the rotation tensor is very much related to the vorticity in this form. The vorticity is given by epsilon ijk. What is epsilon? This is the alternating tensor, right? Alternating tensor multiplied by the omega ijk. Alternating tensor multiplied by omega ijk, which is the rotation tensor. So that is how the vorticity and rate of rotation tensor are related. So that's the background about rate of rotation tensor and the rate of strain tensor. The rate of strain tensor is Sij, which is symmetric, and the rate of rotation tensor is omega ij, which is anti-symmetric. Now let's look at some transformation properties. Some transformation properties are illustrated through figures in this slide. In terms of, so if this is the reference, the first figure is the reference. What happens if you change of scale, if you do a change of scale? So as you can see, it has increased, transformed in size. What happens if you shift in space, as shown here? What happens if you change in orientation? You rotate it. What happens if you reflect it? If you have motion, what happens? If you have acceleration and if you have a frame rotation, what happens? So let's look at these scenarios and what happens to the Navier-Stokes equations in case you have these transformation properties. So we'll start by looking at a concept called the Reynolds number similarity. So this comes from dimensional analysis. If you consider 2 experiments, and let's say the second experiment is performed at a different time, different location, different orientation, say moving platform for a different fluid, on an apparatus that is geometrically similar to the first. Again, geometrically similar to the first but on a different scale. In that case, the question you have to ask yourself is, are the velocity fields in the 2 experiments similar? Are the velocity fields the same if they are scaled appropriately and referred to appropriate coordinate systems? That is the question. So they can be identical if you scale it in the right way. What do I mean by scale it in the right way? So what I'll do is, I will non-dimensionalize by Navier-Stokes equations. I will take u hat, okay, u hat I component is u over some non-dimensional way, some scaled, some constant velocity u0. So this is ui over u0. Then the same way I will scale my x as well. So xi hat is xi over L0. And my time t, I will use velocity and length to write it as, so this is t hat, t over some constant time scale, some time scale. So that would be L0 over U0. That L0, U0 are what are marked in this fancy L and U on the slide. If I do all of this and substitute into the Navier-Stokes equations, I get my continuity equation that looks like this. I get my momentum equation that looks like this. And I get my Poisson's equation that looks like this. So I had those three equations, right? Continuity, momentum, and the Poisson's equation. And I have now non-dimensionalized it and written it using the scaling criteria that I showed here. So UI hat, the hat variables, the hatted variables are scaled variables and they are non-dimensional, because what you have done is I have taken UI over U0. So I've made it non-dimensional. I have taken XI over L0. U0 is a velocity scale. L0 is a length scale, a characteristic velocity scale, a characteristic length scale. In a pipe flow, that L0 could be the diameter of the pipe. In a flow over a jet, in a jet flow, in a turbulent jet, for example, the L0 could be the diameter of the nozzle. And the velocity could be the incoming velocity of flow, incoming velocity of fluid in the nozzle. So that's what I'm using to scale my variables. And I have obtained the scaled equations. Now, as you can see, these set of equations, when I take it from experiment 1 to experiment 2, remain the same. As long as the Reynolds number remains the same. Because it is the exact same equation. There is no density, there is no velocity, there is no pressure. It's all scaled values. Which means from experiment 1 to experiment 2 to how many ever experiments, the flow can be identical if the Reynolds number is the same. Because Reynolds number is the only parameter that defines it. How did I get Reynolds number? In this particular case, Reynolds number would be defined as your velocity scale L0 divided by nu. So as long as the Reynolds number remains the same, I can scale the values. That's what I'm doing here. That is how I get these values. So the flow can be similar between the two, and the flow can be identical if the Reynolds number is the same, if you scale it. So experiment 1 to 2, if I take experiment 1 and experiment 2, if they are unscaled variables, so UI and UI, they will be similar. UI1 and UI2, these will be similar. On the other hand, if I scale it, I have UI hat at 1 and UI hat at 2. These will be identical if the Reynolds number is the same. If RE1 is equal to RE2. That is the Reynolds number similarity. Now, UI1 and UI2 will be similar if you rotate it, if you scale it, if you use a different fluid at similar conditions, as long as the geometry is geometrically similar. Here, in this particular case, they will be identical if you use the scaled variable. So that is what I'm relying on. That is the Reynolds number similarity, and that is essentially what we say here. So if the Reynolds number of the two experiments are the same, then the scaled velocity fields are also the same, identical, because they are governed by the same identical equations, isn't it? Same identical equations. Because once the Reynolds number is the same, there's nothing that differentiates equation 14 between 1 and 2, experiment 1 and 2. That's what we are saying. So that takes us to the topic of invariance. Now let's say you perform the second experiment at a time later than the reference experiment. Then what happens to your scaled independent variables? It becomes this one. This x hat is x divided by L, which is x minus x. So the apparatus is translated by an amount. So everything just scales. And in the similar way, t minus t, u over L. So if you do that, nothing changes in the equation. So what you're saying is that the Navier-Stokes equations are invariant to translation. Again, with regard to reflections and rotations, coordinate transformations are again Cartesian tensors. So Aij, which is the transformation tensor, is Ei dot Ej. Ei and Ej are the direction cosines. Here again, xi hat is xi divided by L, which can be written as, now using the transformation tensor, it can be written as Aj times xj divided by L. So your newly transformed variable is ui hat Aji uj. All you're doing is multiplying it by a transformation tensor. And again, the Navier-Stokes equations are invariant to rotations and reflections. So this is the invariance property. There's more. Let's say analogous to the reflection of the coordinate axis, let's say I consider a reversal of time. Although that is not practical, let's say for the mathematical purpose, let me consider a reversal of time. Then my new time, t hat, is minus t times u over L. I'm using this u over L just to get time in terms of length and velocity. And then my new u hat becomes minus u over u. What happens here is, when you substitute this into the Navier-Stokes equations, everything else remains the same except for that viscous term, because the derivative is taken twice. Because the derivative is taken twice, this remains, that there is a change in sign in the viscous term. So now the Navier-Stokes equations has changed, has been modified. So they are not invariant to a time reversal. They are invariant to translation. They are invariant to reflection or rotation, but they are not invariant to time reversal. Let's say you have now the last point, let's say you have a moving frame. So then your x bar is x minus vt. Now here the frame is moving, and that is moving at a certain velocity. Here also the Navier-Stokes equations remain the same. So in that sense, they are Galilean invariant. So those are the four things: translation, rotation and reflection, time reversal, and then moving frame. Except for time reversal, the Navier-Stokes equations is invariant to the rest. So what we saw in today's class is we looked at the vorticity transport equation. We derived that by taking a curl of the Navier-Stokes equations. And then we started to look at the Reynolds number similarity. So I want you to understand how you arrive at these, what we call scaled equations or non-dimensional equations, by scaling it using these relationships. If you scale it, you end up with only Reynolds number as the parameter. So as long as the Reynolds number is the same between two different experiments, the velocity fields that you get are identical, are the same. That's the Reynolds number similarity principle. And then we talked about the invariance theory as well, where the Navier-Stokes equations is invariant to scale transformation, rotation, reflection, and even moving frame, but not to time reversal. Thank you.